Hello everyone, this video is about Chapter 5, Continuous Random Variables. We have learned probability distributions for discrete random variables in Chapter 4. Recall that a discrete random variable is a random variable that can only have integers. A continuous random variable is a random variable that can assume any value with decimals. One of the discrete model is binomial distribution with a plot as shown, where x is the number of success and y is the corresponding probability of x successes. The height of a bar is probability. How about continuous probability distribution then? The graphical form of the probability distribution for a continuous random variable x is a smooth curve. Let's see the definition. This curve, a function of x, is denoted by fx and is called a probability density function or a probability distribution or frequency function. The probability that x falls between two values a and b is the area under the curve between a and b. Note that, different from the discrete random variables, equal or not equal is the same, because x equals a is a line, a straight line. Having this line or not, the area between a and b is the same. That is, probability that x larger or equal to a and smaller or equal to b is the same as larger than a and smaller than b. In other words, the probability is the same regardless of whether or not you include the endpoint of the interval. Also, because area over intervals represent probabilities, it follows that the total area under a probability distribution, the total probability of all values of x, should equal to 1. One of the most commonly observed continuous random variables has a bell-shaped probability distribution called a normal distribution. The normal distribution plays a very important role in the science of statistical inference. For example, SAT test scores or IT test scores in a school will approximately normal distributions. Adults' weight or newborn baby's weight will approximately normal distributions. Here is the formula for the normal probability distribution, where x is the x-axis value. Mu is the population mean. Sigma is the population standard deviation. And E is a constant approximately to 2.71828. Later, I will show you how to use the z-table to calculate the probability, the area under the curve. Now, let's see some properties of the normal distribution. Firstly, it is bell-shaped. it is symmetric. That is, the middle is mean, median, and mode, and they are equal. The two tails will never end, extend to infinity. Here are several normal distributions with different means and standard deviation. In the previous chapter, we learned the empirical rule. The empirical rule is based on normal distribution. In Chapter 2, we did some practice to check the data percentage and whether it satisfied the empirical rule falling within 1, 2, or 3 standard deviation. Actually, if the data percentage falling within 1 standard deviation is close to 68%, data percentage falling within 2 standard deviation is close to 95%, and data percentage falling within 3 standard deviation is close to 99.7%, the distribution is approximately normal distribution. For any normal distribution with mean, mu, and standard deviation, sigma, we can transfer it into a standard normal distribution. Why standardized? Because the standard normal distribution is the simplest one. Then, how it can be standardized? By z-score formula. That is, any x value minus mean mu, and then divided by the standard deviation sigma. It will become a standard normal distribution, the simplest one, with mean 0 and standard deviation 1. Any normal distribution with mean mu and standard deviation sigma, you can use this z-score to transfer it into a standard normal distribution. From the plot that's the middle mu to the plot at the middle, mean of 0. Mu plus 1, 2, or 3 sigma will transfer into 1, 2, 3. Because the mean is 0, sigma is 1. Also, mu minus 1, 2, or 3 sigma will be transferred into negative 1, negative 2, and negative 3. So now, let's see how to find the probability in the standard normal distribution using z-table. First of all, let's see the plot. The shaded area under the curve between 0 and a z-score is the probability. In the z-table, the first column is the z-score, first decimal. And the top row is the z-score, second decimal. In the z-table, inside or the body of the table is the area between 0 and the z-score z, which is also the probability. For example, the probability between 0 and 1. So the z-score is 1, 1.00. Find the first decimal, 1.0, and second decimal, 0.00. So the probability is 0.3413. Another example, probability between 0 and 0.66. Z-score is 0.66. So the column and row is like this. So the probability is 0.2454. Probability between 0 and z is equal to the probability between negative z and 0 because it is symmetric. For example, probability between negative 0.53 and 0 is equal to between 0 and 0.53. So the probability is 0.2019. How to apply it to solve practical problems? We will use the Z formula. For any normal distribution with mean, mu, and standard deviation, sigma, the probability that the variable x higher than a number or smaller than a number or between two numbers, we can use the z-table to find out probability. That is, each side minus mean, mu, and divided by the standard deviation, sigma. Then please watch the next video to see how to use z-table for different cases.